Thank you once again, everyone. Now it's over to you, Pradipto sir. Please continue to start our session one.
Okay, thank you, madam. Now I am going to introduce the speaker of the first session, Professor uh, Devjani Mitra, madam. Madam will discuss you on the topic of introduction to next generation communication 5G. Professor Dr. Devjani Mitra is a BTech from BIT Sindri, where she was the second topper of the university. She earned her master's from IIT Dhanbad in the area of data encryption and security, along with a Young Scientist Award of her thesis conducted in joint guidance with IIT Kharagpur. Her PhD from IIT Dhanbad was in an interdisciplinary area of sensor fusion in robotics. She started her career in the instrumentation department of Rourkela Steel Plant, SAIL, in 1990 and subsequently shifted to academia as a lecturer in BIT Sindri from 1992 to 98. She has been serving as a professor of, of the Department of Electronics Engineering in IIT ISM Dhanbad since the last 26 years and headed the department from 2015 to 2018. She has guided about 12 PhD scholars, among IM also is there, and currently 4 are enrolled. She has supervised few projects also. Her research specialized area are wireless communication, 5G technologies, communication networks, machine learning, and statistical signal processing. Her application domains and strong expertise in area of cognitive radio, hidden Markov model, Kalman filter, estimation detection, spectrum sensing, optimization, genetic algorithms, intelligent control, radar tracking algorithm, radio environment mapping, TV white space sensing. Also is there millimeter wave massive MIMO and object re-identification. She has many SCI journal publications in this field. So I request Madam to start this session with his topic on introduction to 5G communication.
Hello,
Over to you, Madam.
Am I audible properly?
Yes, ma'am, you are audible.
Thank you, Dr. Pradipto, for the excellent introduction. So I would like to, I suppose most of the audience are already have joined, so we can start.
Yes, ma'am.
Okay, let me share the screen. Is my screen visible to the viewers?
Yes, ma'am.
Yes, ma'am.
Okay, so I'm just switching off the camera so that the bandwidth is optimized. Okay, so I suppose most of the attendees over here, they are having a little bit of background of wireless communication. I hope so. Okay, so let us start. Although this lecture slot, am I audible or Pradipto? It's okay. I mean the
yes,
audio.
yes, ma'am.
Okay,
yes, ma'am.
okay,
Clearly
okay.
audible.
So actually, the topic of what we'll be just discussing today, purposefully, I have not made it too much of mathematical because the technology of 5G, 6G, etc. that we are going to speak. So in today's lecture, because 1.5 hours is just something in which you cannot explain all the technical details also. And most of the, I think the participants, they are all teachers. So they are capable of, I mean, they are already exposed to the background. So at the same time, I'm not going to make it too boring so that the technical jargon and mathematical equations purposefully I have not kept. But what I guess is that with my little bit of experience in whatever you call, in the little bit of research experience that I have in the area of wireless communication, and it's a huge field which is growing like anything. So even if the moment we are maybe at the end of my lecture in another 1.5 hours, some breakthrough or some advancement is going on very rapidly. So because it's evening time, and I think most of us are almost, the day is going to be over. So I'll try to make the talk as interesting as possible. And please note that all this address to all the audience, that you can interrupt me any way you want, because this is not a conventional lecture. So anywhere, at any point you have any questions or any clarifications, you may just interrupt in between also. I do not have any problem. So I may be knowing the answer, I may not be knowing, but definitely I'll try to help it out to the best of my knowledge. Okay. So what I would be trying talking about, I have about a few slides over here. So most of us, I think we have, even the person on the road who is not even a technical person, they have an idea about, or everybody knows about the words, the buzzwords 3G, 4G, 5G, 6G. So, okay, mainly but I would like to give you some of the overview of what exactly do we mean when we go from, let us say, 4G to 5G and 6G. If you remember, once upon a time when many of us did not have a WhatsApp LTE connection, so we realized whenever our SIM was not working, so we naturally moved to the WhatsApp and started making a call, because that would usually be, much better connectivity, and sometimes it works through. So what actually is the story of 4G? Then we move on to 5G, and coming around on the corner of our next decade is my 6G. So they say that every 10 decade or so, there is a actually a shift from one generation of technology to the next, that is 4G. So near about 4G started in 2010, then around 2020 the 5G started, and then more or less by 2030 6G, right now it is in the research stage, but it is going to take up the, almost at the deployment stage or practical adaptation state, it will start in 6G. So let us see what are the mainly what is the main thing that defines the move from 4G to 5G to 6G? Is it a rapid change of technology, or is it something evolution? So interestingly, it is not exactly an evolution. Evolution means that when 4G stops and you start having 5G, 5G stops and you have 6G. It's not like that something. So it is, what we actually mean over here is the technologies are coexisting. So that means whatever what was existing for 4G, it remains. But there are some additional features which are getting added as we move from 4G to 5G to 6G. So mostly you'll see when 4G started, it was mainly about mobile broadband revolution. We started speaking about broadband when our phones started being used more for data. Earlier it was simple SMS kind of applications. So now gradually we move to streamings and the use of several apps, and it's basically about the excellent connectivity started improving. The moment we move to 5G, 5G has got a very clear-cut roadmap. I think those of you who have got little bit might have gone through any papers or even the basic books of 5G or introduction. You must have come across these terms. So these are typically the three pillars, or what we call the three foundations of FG. We call them the use cases. EMBB stands for enhanced mobile broadband. Then we have your what we call the URLLC is ultra reliable low latency communication, and massive machine type communications. So here you'll see that what we are doing is we are trying to separate the type of data applications that we can have, and the beauty of it is that they are going to exist together. So what do I mean by this? Broadly means here enhanced mobile broadband is mainly about, there are a lot of data communication which requires very high speed. So what is important is the speed. Say when we are wanting to download movies, or let us say we want a high speed of internet connectivity. Okay, we want to make a video call and things like that. So it will definitely come under this type of application. On the other hand, there are some applications which is something sort of an emergency type of applications where latency, what is latency? Latency means delay basically. So it means that we need applications which are very sensitive, something like an emergency type of applications where your what you call reliability of connection is very important. Okay, so when you are, let us say when you are watching a movie, even if there is a bandwidth problem or something, so you don't bother much. Again, you can resume the watching the video after some time. But if it is a robot assisted surgery, if it is being used for self-driving vehicles, then I think you cannot afford to make even a 1 second also delay in some miscommunication, because it's going to cause an accident in the road if a 5G network is being used for self-driving vehicles. Are you getting the point? Remote assisted surgery, if the dead network fails, so there's going to be a huge difference. The person may be dying. Okay. So this kind of application has to be given a other type of priority. The requirement cannot be the same. Other hand, you have the machine, a massive machine type communication. This is typically my low power sensory data, my IoT data, where you have, what the word massive means, you have a large number of such sensors or machines, okay, Internet of Things, IoT and all. So where these are not very emergency type of data. At the same time, they do not require very large bandwidth, but they have a large number. So we can give the analogy, the typical analogy that is there is, suppose in a road. Suppose in a road there are many type of traffic, isn't it? Now, do you have all the traffics are moving together? What happens? Do you think the situation is a good one? So the first one, EMBB will, let us say your normal cars moving at a very fast rate. Okay, so this kind, very high speed cars. Now among the high speed cars also there could be a normal car, passenger car, there could be a sports car. Now does the sports car, will you allow the sports car to travel the same road as the normal vehicles? The answer is obviously no, because it's going to be different type of application. It's definitely going to cause accident. At the same time, if there are slow moving trucks moving along with the fast moving vehicles, once again, you will have a lot of problem in adjusting the traffic, controlling the traffic. So definitely, and let us say you have small bikes also. Bikes are, because in bike in one lane, only one car may be going. But if there are bikes, 2 or 3 bikes may be going parallelly in the same road. So something like that. So are you getting the point that you may have, and obviously there'll be a large number of bikes on the road. These days you find a large number of bikes on the road. So the analogy I'm trying to give is that 5G is clear cut, clear about the application, which type of application it is being used. So it is being used for smart grid. I think many people might have heard about smart cities, smart grid. Everything relies on a good network of sensors. So they will come under the third category, whereas very emergency type of applications will come over here. So now there is one principle that does this, is called the network slicing. This is the network slicing means it's something like you separate the applications and give different type of lanes or different type of control for this. So you identify, okay, there's an ambulance in the traffic. So the ambulance has to reach earlier than, let us say, a truck carrying some cargo. So definitely, so it needs to reach earlier so that the passenger can be saved. I mean, the patient can be saved. So I'm just giving an analogy. So similarly, your internet traffic also has to be classified accordingly. You have different types of networks. So network slicing is the term that we use. That is the what is making the 5G possible. So initially 4G, the technology was OFDMA. The green represents mainly the main technologies that is covering the 5G. Okay. Now when we move to 6G, you can see a big role of AI, or what we call machine learning. AI is coming into taking. I mean, my air interface is now getting more intelligent. Okay. So, and the frequency range is also going much higher. So something called reconfigurable intelligent surfaces, they are still not under deployment stage, but these are in the borderline between 5G and 6G. So these are some of the technologies. All these are huge areas and very difficult areas, but at the same time, these are the areas where research is happening right now. 6G, as I told you, it's a system where you have, just a minute, I'll just move this. Where the technologies will, please note that these technologies will not be replaced, but they will be enhanced to enable immersive and pervasive connectivity. It is something like you will feel as if maybe sometimes we are actually having a video call with your some other person, you are having a video call, but you know very well that the person is, let us say, at a much far distance. But then this, the what you call the boundary between the physical world and the digital world will gradually dissolve. And you'll almost feel like, suppose you're talking with your parents or with your children or some brother, sister who is staying in a US or in other part of the world. So almost you can have, and he's having dinner. So you can almost feel what, as if you are sitting with them and dining, or maybe whatever meals they are enjoying, you may even get the flavor of it. Okay, so there will be a lot of sensing, lot of AI, virtual reality, augmented reality, which will be totally integrated into the system. So please note that the technology is not changing, but gradually as we are moving, new features are getting added. We start with, I think most of you are having an electronics background. I think we all identify this great relation. This is known as the Shannon's capacity equation. All of us recognize this. C is the channel capacity. B is the bandwidth. What is this? This is my signal to noise ratio. So whenever what happens is that the main problem is starting with the capacity crunch, which means that as the explosive growth in data is increasing, we want from 4K to 8K, we want to move into higher resolution video. IoT is coming, your metaverses, your entire streaming social media platforms are coming. So everywhere, I think with the amount of video people are watching, downloading, and YouTube channels and all, so you can imagine the growth in data. But here, please note that my B is already exhausted. We are right now, we are in the, as long as we are in the 4G or just beginning of 5G, etc., we are mostly in the sub 6 gigahertz range, sub 6 gigahertz. That is where most of our mobiles are working. Okay, so typically you have 100 or 200 megahertz of bandwidth spectrum. So, but now this is already congested. So this B is now getting exhausted. What is this signal power? Signal power is also in wireless communication. We cannot increase, in order to have a high C, we need to increase the signal power. Now that is also not possible to increase too much because it will create interference in the wireless domain. We have this is my noise power or interfering power. Now this is huge in case of wireless because there are large number of users. Everybody is contributing to some. So the one step that we are making is that we are moving from the sub 6 gigahertz band to the millimeter wave band. Millimeter wave band is approximately the 24 to 100, not the frequencies. It's roughly 24 to 100 gigahertz. So this is still not used. So people are now have begun to move this. So where typically now we have identified about 2 to 3 ranges of bandwidth that works quite well. That is 400 megahertz bandwidth. Can you just compare it with the sub 6 gigahertz? So from 100 to 200 megahertz or even below, before that in 4G and all, we had a simple 20 megahertz bandwidth. From 20 we moved to 100, 200. Now in the millimeter wave we are able to get 500, 800 or even 1 or 2 gigahertz wide bandwidth. So you can definitely you have a huge scope of increasing the bandwidth and thereby improving the capacity. Sub 6, if you always you'll find this comparison, they will always compare it to the road system. So it is just like sub gigahertz is a massive highway system. Okay, it is very, very reliably, the connectivity is very good because of frequencies. What is the main difference between the sub 6 gigahertz? It's typically around 1 gigahertz. Normally our phones that we are using these days. Okay, so they have a range which is giving us a good amount of range. Okay, because your signals are passing through a lot of tunnel, mountains, etc. But look, what happens is that when we go to millimeter wave, definitely it is catering to high capacity because bandwidth is increasing, but there are some problems. Okay, because you don't get anything for free. So if you are getting something, definitely there is lot of other problems will come up, which we'll be subsequently discussing. But there is no other way that we can go because sub 6 gigahertz is already exhausted. It is almost finished. So we have to go into a higher frequency band, and millimeter wave is the only place where we can find enormous amount of empty space. So in order to increase the capacity C, I have to increase the B by going to the millimeter wave band. Okay. Now we cannot do anything about the signal power. I don't want to increase the power as I told you, because wireless may, if you increase power, it is going to be creating havoc. So what we do is we try to reduce N, or the interfering noise. Okay, so that one of the breakthroughs that actually made possible my 5G, it is as I told you, it is a millimeter wave. So you have a massive bandwidth. You can get channels of hundreds of megahertz wide. Okay, only 20 megahertz was available in 4G. Compare it to the, gradually we have moved down almost to 1 or 2 gigahertz. But as I told you, the biggest challenge of millimeter wave is that the path loss is very high. Sensitive to blockage means the earlier sub 6 gigahertz ranges, they were actually, they could penetrate your walls, tunnels, rooms, buildings. But here, the blocking is very severe. Even your hands or finger, I mean, if you just put a hand on the millimeter wave, electromagnetic waves, so it cannot penetrate the hand also, because this is because of the wavelength. So the wavelength of your hand wavelength is actually slightly more than the wavelength of your millimeter wave. So that's why it's not able to cross it. But then we have good solution to overcome these challenges. One of them is the beamforming. The other one is what we call the dense networks. Dense network means we make, instead of a large cell, we make small cells. Okay. So this also actually helps us to, some of the challenges we can overcome. Beamforming is one of the breakthrough technology, or it is the main, what you call the power behind your 5G and beyond. So as we talk of, once again, please note that sub 6 gigahertz is where we were in the 4G, and millimeter wave we are gradually moving towards in 5G and 6G, because there is no other way at that we can increase the capacity. Okay. So but please note that it's not that we can just discard sub 6 gigahertz and move into the millimeter wave. So if you look at this table, I hope this table is visible. Can you see the trade-off? I think you understand the meaning of the word trade-off. Trade-off means when you gain something, you also lose something. It's like doing a business. Okay. So can you see what we lose and what we gain? Definitely my coverage and penetration power is very poor for millimeter wave, but it is excellent for this. But look, the first 2 points you can see are very good for the sub 6 gigahertz. So kilometers, compare this to only a few meters. So the range is very poor. Okay. That means your millimeter wave is going to be attenuated in a very short distance. The capacity, whereas the latency, I told you the delay. This is somewhere I think we were discussing about the 5G application. So latency is a very important. Latency means delay. So extremely low delay is possible for my sub 6 gigahertz. But then again, we cannot leave this and go into the others. That means we have to take a switch over. That's what we call it as a heterogeneous network. That we may use this frequency also, we may use frequency also. So that type of heterogeneity is possible when we are moving or when we are coming to the 5G network. So it's very, very powerful control is there. So what we do is we have a macro layer, sub 6 gigahertz. It's a large cell tower. Okay, so it will mainly provide, let us say in a building, it will provide a blanket of 5G coverage across a very wide area. So this is important for connectivity. But then for some areas where I told you the why small cell, because millimeter wave range is very small, a few meters. So within the large cell, we also introduce small cells. These small cells will work on millimeter wave. So something like in some specific areas, maybe you are not getting good network coverage or something. Okay. So they may be, but where you need very high speed streaming. So there perhaps where more than connectivity is that we need a very, very high capacity. So in those places we can shift to sorry, excuse me. Okay. So this is what is the meaning, that we have a main macro layer and followed by a small sublayer. If you see once again the comparison, the main difference between, there are certain properties in which this is very important to understand millimeter waves, because most of the technologies that are there for MIMO is actually related to it. You can see that millimeter waves they are more similar to the visible light. These are higher frequencies, isn't it? This is the range, typically 24 gigahertz from 3 gigahertz, I mean from 30 gigahertz to 300 gigahertz or something like that. We typically try to 24 gigahertz is typically the workable millimeter wave range. So can you see, if you compare with the properties of visible light, they are almost most of the properties are very, very similar to light. See, they travel in straight line. So you don't always have a LOS path. We need an LOS path. Please contrast this with the radio waves, 6 gigahertz. They have a power to diffract around obstacles, but these two are in straight lines. Similarly, diffraction is, that's why we are getting our mobile signal, because our signal can actually bend around objects and reach you even inside your room, inside a building or something. But millimeter waves, they are blocked. They will be reflected just like light. They will be reflected or absorbed. It's just like light. The properties are more towards the light as you move in the electromagnetic spectrum. Beam forming, it is difficult. This is one of the advantages. It is difficult to make precise beams because the signals are spreading out more like an omnidirectional antenna. But here you can form a beam. So this is actually like a laser beam. Okay, like light you can form with a torch light or a flashlight. So instead of something spreading, or a floodlight, have you seen floodlight on the fields? They spread the light on a large area, but at the same time you can have torchlight. So these things are possible with millimeter waves, which is not possible with this. So this is also one of the background why your technology is working. The second breakthrough, so first breakthrough that we talked about is my millimeter wave. The second breakthrough that we are talking about, which is actually has ushered the era of 5G, that is my massive MIMO. So what is massive MIMO? Please see, this is just the Shannon's equation that we talked about. Okay, this is my bandwidth. W is my bandwidth. W log 1 plus SNR, the SINR. SINR stands for signal to interference noise ratio. Okay, as I told you, in wireless we'll have a lot of interference. So here the capacity equation gets modified by two factors. I think this part is common. One is my M. M stands for the number of antennas. So if I'm using 100 antennas or 1000 antennas, the capacity is directly getting multiplied by that factor. And here is that when I'm using the small cell deployment, I talked about the small cell layer, large number of small cells, dense network. So that means this will increase the number of access points, base stations. So directly we are able to, I mean, this is a simplified version of how the capacity multiplies. Okay. And if I'm able to reduce the interference, see, I cannot do anything about the signal power. So when I have a signal to noise power, I cannot increase the signal power. So what I do is that I reduce the noise. That effectively increases my SNR. So that is also increasing the capacity. So this is the approaches where massive MIMO is actually helping me to expand. This is going to be a part of the network. The rest of the things you can do. So base stations with a very large number of, what is massive MIMO? When I'm using, instead of few antennas, I'm using large number of antennas. Typically, I think 64, I mean, typically we use 64, 128, 256. These are the typical number of antenna elements. And antenna elements, we realize not physically antennas, they are all array antennas, antenna arrays, where you can have the number arranged in a particular pattern. Okay. So those of you are, I'm not going to discuss because each of them requires as a special lectures which will require, but at least if you want to get into 5G research, you should be understanding these basic terms. So how does a massive MIMO achieve spatial multiplexing? Spatial multiplexing physically means, see, without changing the bandwidth, if you see the original equation of B and SNR, so without changing B, without changing the signal power, signal to noise ratio, anything, at the same time, I am able to actually transmit same time and same frequency resource by directing the beams. Okay, so that means if there are 100 users, the base station is sort of going to produce 100 beams, each of them directed to the 100 users. So you get your own beam. Okay, it's almost like a personalized service that you are getting. This is possible through massive MIMO, and beamforming is the technology. This is one of the main workhorse of the thing. 3D, because then you have different directions. From beamforming, we come to 3D beamforming, which are typically used because now we can estimate the channel in 3 directions. The 3D channel models are used. Horizontal means left, right. Vertical means up, down also channel, as well as your signal power varying in the 3 directions. Okay, so 3D beamforming is possible, and very, very precise beams can be actually generated. So actually millimeter wave is actually providing us the bandwidth, and massive MIMO is providing us the capacity for precise steering, or what we call the beamforming. So it allows basically the data to be sent reliably to the different users. So it's something like, let us say, the millimeter wave technology is providing us the wide road, a big highway, okay, or where you can actually divide that highway into, let us say, 100 lanes or 4 lanes, 5 lanes, depending on this, and then everywhere, so that the traffic congestion is not there. So maybe one road you reserve for one type of application. So there could be a emergency road. There could be a different road for bikes. You can create flyovers where some vehicles can be, or some data can be actually can overtake and go on a different way. So this kind of control, everything is software controlled. Okay, so we have software defined network which actually overlays this. So to sum up, actually, so ultimately we talked about the capacity. Okay, so capacity is proportional to the number of spatial streams. Please see this capacity equation. I'm just qualitatively, I've tried to analyze without any mathematical equations. So capacity is proportional to the number of spatial streams, okay, into bandwidth and spectral efficiency. What is spectral efficiency? Spectral efficiency means the bits per second per unit frequency or per unit hertz. So bits per second per hertz multiplied by bandwidth will give you the data rate. Okay, bits per second. And then if you are using only one without MIMO, the number of bit stream will be 1. But you can increase the spatial streams. It is like parallelly, simultaneously, I can send 100 beams, and none of the beams are going to interfere with each other. There will be dedicated beams sent to different users. So effectively what you are having is, we call it something like the cloned highways. Okay, that means instead of one lane, you have several lanes, and these several lanes can be used simultaneously without any collision of data streams. So they are orthogonal data streams. This is nothing but some signal processing algorithm. This is exactly the massive MIMO multiplier factor. Okay, so this is MIMO is going to give me, so can you identify this number of spatial streams can be increased by MIMO technology, the bandwidth can be increased by millimeter wave technology, and spectral efficiency normally is handled by the modulation technique. So a practical example, let us say we have a 4G cell. You can just compare how the capacity difference comes between a 4G cell and a 5G cell. A 4G cell is having 4 spatial streams, let us say. So maybe I have a 4x4 MIMO. So it's having 20 megahertz bandwidth typically, because I told you there's a only limited amount of bandwidth in the 4G sub 6 gigahertz range we were talking about. So effectively you have only an 80 megahertz bandwidth availability. The moment I'm moving to my 5G with millimeter wave and massive MIMO, so this massive MIMO is producing 16 spatial streams. Okay. And 800 megahertz is a typically bandwidth, suppose. It may go higher to 1 or 2 gigahertz also. So what is the total? Can you just compare 80 megahertz to 12.8 gigahertz? Straight away, we have a straight away expansion of capacity. So almost 160 times wider than the 4G cell you are getting. So sub gigahertz 6-week frequency, typically 64 antennas was the usually practically is in most standards it is used, 8x8 grid. This is the antenna grid. Okay, it's an antenna grid. You must have seen some pictures of how the base station MIMO antennas look. Like a square array antenna arrays are there, phased antenna arrays. So 64 antennas are used here. Millimeter wave, typically we have practical systems in 5G employing 256. So arranged in 16x16. So this is going to make 256 number of 16 into 16, it will make 16 spatial streams. That is exactly how I am getting 16 spatial streams. Okay. Then we can also change the polarization. That will also increase our what you call the capacity. Please note once again that we need both massive MIMO and millimeter wave. There's something like they're almost like husband-wife marriage partners. So one without the other is actually useless. So without massive MIMO, if you just use massive MIMO, millimeter wave is useless because the signals would be too weak to cover any practical area, making commercial deployment impossible. Why is this happening? As I told you, the physics of millimeter wave is that its range is very small. Then a lot of atmospheric absorption happens. The range is small, the attenuation is large, penetration power is very poor, so it's not going to work beyond a few meters. So in order to increase this, the only way we can do is by adding massive MIMO, and which allows beamforming. Using beamforming, we can actually solve the problems of, it is something like millimeter wave, massive MIMO is solving the challenges of millimeter MIMO and vice versa. That whatever challenge of massive MIMO is there, without millimeter wave, that cannot be removed. Okay, because your the basic bandwidth has to be available, isn't it? For example, you want to build a skyscraper. Okay, so but for to building you want to make a apartment with having 15 floors or 20 floors. So for that apartment, you first need a land, isn't it? Now within that land, you can have a big design. You can have a 15-story buildings, or you can have 25-story buildings, but basic land you require, isn't it? So that is what something that we say that the already sub 6 gigahertz bands are already crowded. But in order to increase that transformative potential, we need the basic land or the basic background bandwidth, on top of which you are going to build the MIMO system. So together they are forming the technological backbone of true 5G. Okay, it's something like the millimeter wave, if we give the analogy. So millimeter wave is actually providing us the highway. Big highway it is providing, the road. You first make the road available, a vacant road. Then only now the massive MIMO is nothing but signal processing. So different problems on the road, somewhere the road the structure could be different. Somewhere you can do a lot of other things. So those things, massive memo, signal processing in massive memo can be used to solve the problems on the road, how you develop the system. Okay. So your, for example, you want ultra dense IoT. What type? Here, the once again, as I told you, please remember, the beginning only we talked about the 3 pillars or foundations of 5G on which it is based. So AR, VR means your augmented reality or virtual reality. You are watching a music concert. Some very renowned musician is playing. So you would like to, but you cannot be in that. But actually, with augmented reality and virtual reality, you can actually start feeling that you are actually sitting in one of the audience and enjoying exactly the same kind of this thing. It's not a recorded thing or a live streaming that you are hearing. It's almost like on a live concert. You are sitting on the cricket stadium and actually watching a map. So this kind of applications is possible when we are taking the advancements of 5G. Okay. So the combination that we have is the combination of millimeter wave plus massive MIMO is a huge, revolutionary combination. Okay, so one without the other is useless. So when we are combining them, so there are many antennas. So when we, if you want to go into the deep research of these, you have to understand what is the meaning of why do we have so many antennas, mathematically how the antennas are actually related, how the channels basically change, channel matrices, and how the technology is involved. The wavelength, now when the moment it is combined with millimeter wave, as I told you, typically the practical deployment working frequency of millimeter wave is 28 gigahertz. If you calculate the millimeter, just if you divide it by 3 into 10 to the power 8 meters with the velocity of light, if you just divide, you'll get, typically it is coming around 10.7 millimeters. So even your hand is typically about, say, let us say, 50, you can imagine your 10 millimeters. So this is roughly the size of a finger or something. So even with your hand or your finger is sufficient to block a millimeter wave. So how are you going to use communication with it? The only solution is what we call beamforming. So beamforming is the masterpiece of actually making my system work. So you need a precise beamforming. It's a massive MIMO which controls the precise phase and timing of the signal. From every tiny antenna, it creates a very strong beam or wave which is pointed directly at your phone. So your location can be actually found out. So and then when you are mobile, you can actually move. So even if you move, the beam will also move along with you. The beam steering vector, the orientation. So as a 3D beam, it's something like a torchlight which is moving, and always you are moving in a dark room. And whenever you're moving, the torchlight is actually tracking you, so that continuously you have the good connectivity. So this is the essence of beamforming physically, but it's a complex signal processing algorithm. So if you want to work on this, most of the work is happening on this. Beamforming is already an established technology, but a lot of research is still going on as we move from 5G to making preparations to move into the next, because 2030 is not too far away. And big countries, I mean developed countries, are already established your 5G very nicely. And then they are actually moving into what you call your 6G. Speed. Wonderful thing is that we all need speed. The moment, and I think everybody knows this, that as we are moving from 4G to 5G to 6G, it is the speed which is making a difference. You know, as I told you, the speed is possible because you are getting a very large bandwidth. How much were you getting in your 4G and all? You are getting only 20 megahertz. Now you are getting almost 400 to 800 megahertz. And even practical deployment is with this, even with 1 or 2 gigahertz also. Yeah, people are actually researching. Okay, so it allows for almost GVPS level of, depending on the modulation schemes you are using, you can get almost GVPS speeds in wireless mode. Okay, so network capacity handling, also a lot of research is going on network capacity. Okay, so even if slight differences is there in the physical location of the users, okay, even a few centimeters of separation is also there, the resolution of locating you is very strong because you are using a high beam, highly precise beamforming with millimeter wave technology. So this kind of, and with the heterogeneous network conditions, your location can be, even if with another user, you're in a crowded, let us say when you're in a crowded stadium or an airport or a railway station, where other users are very close together, isn't it? But then still, is it possible for you to have a different beam than your next day neighbor? Maybe your friend is sitting beside you with his mobile and you are sitting with your own mobile. Both of you are sitting together, I mean, just side by side in a train. okay, on an airport, on a crowded place. Even then, very precisely, your location can be actually certain, and then a this beam can be sent to you. So this is the background magic, so-called magic, that happens when you're using the 5G technology. The word massive, it's actually, interestingly, when I'm using massive number of antennas, it is actually making your signal processing easier. Okay, once again, I'm avoiding the technical details of going into this. Okay, those who are interested in whichever area, you have to, but why I'm telling you, if you're interested to go into the 5G research and all, you have to start with making your concepts right up on how these background technologies work. They are very basic things, but then because the technologies are advanced, so you have to understand that the main powerhouse is my beamforming. Okay, massive MIMO is using hundreds of antennas to perform advanced behavior. How it is working? It is something like I was telling you. Let us say you have a tube light in your room. The tube light is actually flooding the entire room. Okay, it's analogous to an omnidirectional antenna. But on the other hand, if I use a laser beam, so it sharply gives a narrow beam like a flash, a laser pointer. Okay, so instead of a flashlight or a laser pointer is much better than a what you call a floodlight kind of thing. The same thing is happening. Okay, so the beam forming is characterized qualitatively by the gain. Okay, we call it the beam forming gain. This is as good as a something like 20 to 30. This is a huge gain. It's almost acting like a powerful amplifier, just like I told you now, the main problem of millimeter wave is that the signal attenuates very fast. So I need to amplify that signals very frequently. So using this, what happens is that you get almost a very good, what you call in the air, you have something called a very powerful power amplifier. So a gain of 20 to 30 dB is a huge, okay. So it is compensating for the high path loss of your millimeter wave. Another just recall, we told that another huge limitation of your millimeter wave signal was that it range is very small, okay, only a few meters, okay, maximum 50 meters, 100 meters maximum, okay. So to make it commercially viable, it's very difficult, because the frequency, higher is the frequency, what happens is the attenuation is going to be more. So once again, the only solution to compensate is that I'm going to have a beamforming, a steering beamforming electronically. Here electronic mainly means signal processing, through signal processing algorithms. And incidentally, higher is the number of antennas, the task actually becomes simpler. It becomes very very easier to make orthogonal beams. That means beams that do not interfere with each other. Okay, so massive MIMO is a technology that makes the millimeter wave usable by overcoming the, I told you, it's a physics of the millimeter wave is very bad, very challenging. Okay, it's because you have a lot of range is poor, Brochet penetration is very poor, range is poor, loss is high. All these things can be addressed with precision focusing using the beamforms. Okay, there are two other phenomenon which is actually related to my massive MIMO. Okay, so if you are going into this area, you must know what is channel hardening. Another related phenomenon is what is called favorable propagation. Favorable propagation means, as I was telling you, that different multi-users are there. Now, multiple users are we are typically now facing a situation when multiple users are trying to access the same wireless channel. So their orthogonality among the users is very important. Okay, so this is a type of favorable propagation. We have to study the channel. What kind of channel is there? We have to make the channel a favorably propagated channel. These are some of the technical terms. I've avoided the mathematical equations. Channel hardening is just the opposite. You have individual fading paths. It's something, uncertainty of the paths is reduced. Okay, the overall channel, because you don't know, na, whenever I'm using which is going to be the path, multipath. Those of you know wireless communication, you are already aware of, maybe at your BTech level or master's level, you must have studied about multipath propagation. So they are all randomly, which path is going to be taken, you don't know. So that has to be addressed. Otherwise, you'll never be able to achieve what I was telling you, that every user, even separated by a small distance, as closely you are sitting, you have to have separate beings from them. So you have to reduce what you call the channel uncertainty. Okay, that is what is channel hardening. So beamforming is the most important technology that is important in your millimeter wave. Okay, so you have what you call high path loss. Let us just sum up why it is important in millimeter wave. Mainly the three main points that we are speaking is high path loss. millimeter wave signal, as I told you, they attenuate or they weaken dramatically over very short distances. Poor penetration, as I was telling you, even by walls, windows, small trees, etc., rain, even a human hand is sufficient to stop your penetration. I mean, the web will be blocked. So how do you address all this? Short range. These are the three main problems of millimeter wave, where beamforming becomes the only solution which can take care of all the three. So what is beamforming doing? It is using multiple antennas. This is where my MIMO has to be, multiple antennas has to be integrated. Whenever I'm using millimeter wave, it's definitely giving me bandwidth, but then I have to integrate it with the what we call multiple antennas to shape and focus into very narrow, powerful direction beams. Okay. So once again, as I was giving you the analogy, that your millimeter is just like a vast empty plot of land you have outside the city, perfect for you want to build big building. But then first step will be I must have the land available. So millimeter wave is giving me that bandwidth over which I'm building my network in 5G network. The next part comes the architecture, because once you have the land, I have to build the buildings. Now you want an advanced architecture, you want to build a very smart city of smart buildings and all. So then you have to use technology. You hire some architect and engineers who will actually build a stable system. The skyscraper should not fall, all sort of facilities should be there, isn't it? So these kind of so you can say that beam forming is actually the advanced architecture and the engineering required to build the stable skyscraper. Okay, so as I told you, the three problems, how beamforming is solving, it is overcoming the path loss by providing a gain, a huge gain from 20 to 30 dB. It enables tracking, as I was telling you, even if the user is moving, so the beam can actually be steered to track a user's device as it moves. And a strong connection with the base station will be maintained without any physical movement of the antenna. You don't need to move the antennas for it. So what is happening? The magic is what we call the phased array antennas. So antenna technology, or what we call antenna technology, or what we call how the phased array vectors, you can actually calculate the how much phase shift or how much gain individually elements has to be given, so that the complex, it's a combined beams of several users can be transmitted together, but they will be going to the separate users. This is where a very strong signal processing algorithms are there. So if you want to understand millimeter wave 5G, you have to start understanding the mathematical background of beamforming. Okay, it definitely reduces interference. Okay? We were calling about what we were speaking about the Shannon's channel capacity, isn't it? So that Shannon's channel capacity, it is for reducing that signal to noise ratio can be reduced by reducing noise. Signal power we cannot increase. We are stuck with a fixed power. Okay, because if you increase power, you are going in wireless may we don't allow high power, because you will start interfering with other users. Okay. So what we do is that you to reduce interference, because you're focusing, the energy is also saved. You know, we are almost, the focus is on energy efficiency, green communication and all. So beamforming is also giving us a platform of saving energy, because energy is focused on specific users. It's not spilling over, isn't it? When I'm using a torch, let us say a tube light. So sometimes what happens, you want to study a book, or you're studying in your study table. Do you need a tube light? Simply if I put a what you call a table lamp, even if the room is dark, with a table lamp I can read, because it's a sufficiently a strong power table lamp has having a lamp. So it is focusing on your book and you can read. With a night lamp or a strong reading lamp, I don't need the tube light. So if I'm using a tube light, so it's actually wasting energy. So I need a focused beam. So that is why energy is focused on a specific user. So it is not spilling over and causing interference for other users. This allows for spatial reuse of the same spectrum. So the same frequency can be used at a different, just it may be your neighbors, somebody who's staying in just beside your flat, they can use the same spectrum. Okay, so that is why how effectively it is actually being used for increasing the capacity. Same frequency, same time, because the beams are separating you and the other users in a multi-user architecture. So are we okay? We are into the 50% of the lecture. Any questions till now? if there are any, I can have a small break. I mean, have a 5 minutes break for inviting any question, then I can move on till now, because otherwise, at a time, if I say too much, so it's just 50% of the lecture. Anybody wants to speak or have a question till now? I'll just wait for a couple of minutes if anybody wants to ask. Okay. So we move into the next part of it. So beamforming, we understand it solves the problem. So beamforming is the essence of it's the main technology or the main software signal processing that is taking care of most of the challenges. So it is something like a filter. What is it filtering at a different, as if key in certain areas of the space, we call it space division multiplexing. So the same, just like you have frequency division multiplexing, time division multiplexing, CDMA, code division multiplexing. This is the fourth dimension which we are multiplexing. It is called the spatial filter. So the core idea is that a wireless signal is basically steered in a specific direction towards a specific location. Once again, avoiding the mathematics of it physically or what is happening, what is the principle of beam controlling? It is basically controlling the phase and amplitude of the signal. Every signal is a electromagnetic wave A cos omega ct phi. So for a given frequency, it has the amplitude and the phase. So what you can do is that the phase and the amplitude of the signal from every antenna element in the array can be controlled. So we can make, because see, I think most of you who have studied multipath propagation, you know that the waves can interfere constructively and destructively. For example, two sine waves, if they are added at 180-degree phase difference, they will cancel each other. Isn't it? So, but if they are constructively, they are added at the same phase, they will actually increase the signal strength. So this is exactly what we try to do. We try to carefully control the phase and amplitude so that the waves constructively interfere in a particular direction and destructively interfere in others. This is what is creating the focused beam of energy. Now, I've told this in a very lucid language without involving any mathematical equation, but there is something called pre-coding, and then you calculate the beamforming vectors, the weights with which the coefficients are generated through the pre-coding algorithm. Something called singular value decomposition, etc. is there. We decompose the, we need to estimate the channel. So those are the intricacies of the background that we have. And then after that, using those weights, we calculate, the algorithm calculates the phase and amplitude. So it's basically just manipulating the phase and amplitude of the signals, and then you are sort of manipulating them so that when they reach, they actually add up in the proper phase and they don't cancel each other and cause my signal to fade. Okay. The primary goal, once again, is very simple to understand. It is only the path loss. I'm using millimeter wave, so high frequencies are there. So high frequencies mein path loss is very high. So it is for improving the signal strength. So it's a very simple concept. Only thing complex about it is beamforming if you want to understand it as a signal processing algorithm. But once the beamforming vector is formed, the idea is very simple. The key analogy I've been talking about, something like if you have a floodlight which is illuminating the entire room like an omnidirectional antenna, instead of that I'm using a directional, very, very highly directional antenna. And how are you calculating the direction of the antenna? Using some signal processing by taking feedback of the channel. Okay, it's a complex process. You first estimate the channel, take the feedback from the receiver. Then there is a pre-coding algorithm with which you are doing this. So I'm just omitting that background. So you can see without beamforming, so there are so many aspects. There are so many aspects that we have when we actually come. This is the main technology that is making the giving me the solution. Can you just, I've given a very good comparison of what happens when you do beamforming and when you do not do beamforming. So the energy is a wasteful broadcast. Here you have a very highly efficient when you don't waste unnecessary energy, because everything you're focusing on a particular user. Otherwise, Joy, they are not only causing interference, they are also causing my wastage of energy. So you have a targeted delivery. Okay, interference without beamforming is uncontrollable. High amount of interference you will get. Here you can manage spatially. It's something you can imagine. You have just you have got several beams. Suppose there are 100 users in a particular area very close together. You have 100 different beams from the base station, each reaching every user. Okay, that is exactly what we called spatial. It's acting like the space is acting like a filter. So it is not allowing all the beams to go everywhere. So it is filtering. Okay, this beam, user one is there in that particular area. This is the optimum beam that will go from the base station to it. The user capacity, the biggest gain is that what we call, as I was telling you, space division multiplexing. The biggest advantage is that you have what you call a very, very high, with beamforming, you're able to achieve very high capacity. If you remember, I mean, basically, if you have so many, I'm going to use 1,000 base antennas, which happens in massive MIMO. So 1,000 times the capacity is going to increase. Range, can you see by how beamforming at millimeter wave, the range is very short. Here, due to the high antenna gain, the beamforming is giving us a very long range. So almost few kilometers, you can expand the range from a few meters to few kilometers. The coverage is static and full cell is used, but here it is dynamic and user specific. But of course, you need to have something like a radar. Continuously, it is estimating the channel, managing the beam, finding the best path, and then manipulating the beam to find. And sometimes we'll soon discuss, this is a very important concept that is just beginning to be adopted in the 5G and 6G. That is what we call the RIS. So even without a, RIS is still not practically deployed, but we'll see what happens. So continuously, I'm trying to increase the channel path into a very, very focused beamform so that every user directly gets access to the signal from the base station. Of course, hardware constraint, those of you who want to learn a little bit of beamforming, you will definitely come across the term of hybrid beamforming. We have analog beamforming, we have digital beamforming, and when we are combining both, we call it as hybrid beamforming. Analog beamforming is very easy. It is very cheaper. You simply have some analog phase shifter. I told you now what it does is simply controls the phase and amplitude. Physically, it is very simple. I just need to change the phase and amplitude of two sine waves so that their phases are aligned and you get a very high strength signal. Okay. So what you do in hybrid, you group the beams into clusters. For example, let us say 5 beams are grouped into one cluster. So suppose there are 10 beams, there will be 2 clusters. And for every cluster, we have a what we call a digital beamforming. Digital beamforming is very powerful, but it is costly. So we have a hybrid thing so that we can have a control of the a few digital chains controlling many cheaper. So many, I was telling you, 5 analog phase shifters will be combined and formed a single digital. So that way you keep a make a hybrid beamforming. This is related to the hardware constraint of actually implementing it. So if you want to go, I'm just, my purpose of my this lecture is to help those who want to gear their research into 5G and select a good topic, maybe for doing their PhD or higher studies, etc. Isn't it? So these are the areas that you have to look for when you actually go. So these are typically the situation of a 5G and beyond. Okay. So this is how a massive antenna looks. It's a array type of antenna. Okay. So for example, this is a 4x4 antenna. So every antenna is able to create simultaneously this kind of beam. So if there are 3 users, you can see orthogonal beams. None of the beams are interfering with each other. So there'll be this user, this and this, even though they may be close together, they are not interfering. So you have a very good quality of signal and you can then manipulate the beam. So if one of the users is moving, the beam also moves continuously. You can understand the role of the network. So this is the heterogeneous network where I was telling you the macro cell uses still the 4G sub 6 gigahertz things. As you move into the smaller cell, it is more about using millimeter wave because the smaller is the cell, the range is small. So naturally, it is suited for millimeter wave. So this kind of heterogeneous networks you'll find the broadly what is happening the in a typical 5G network scenario. As I was telling you, something like a network slicing is very important. Network slicing is the magic that actually is because you have different, we talked about 3 main foundations. What are the 3 main foundations? We have 3 types of traffic. One type of traffic is very high, high data rate is required. Okay. But then the speed is important. Second type of application is type, as I was telling you, some emergency type of applications where my latency is important. Third type of application is that you have low power data, okay, but you have them in a large numbers. So suppose I'm wanting to set up some smart city and all. So based on the sensory data, they all are going to use the same 5G network. So it's something like in a traffic system. So you cannot have all types of traffic together. There will be a lot of traffic jam. Na? Suppose some slow truck is, some trawler is a huge trawler is coming in between, and sports car and all types of cars are there, and then bikes are also there, cycles are also there, many cycles. So this kind of situation has to be done. The network has to be sliced according to the different types of traffic. Broadly, it is done through the three types of traffic in 5G. So what it creates is, it creates virtual networks. No physical separation, isolation is done. Okay, it is through software. We logically, just like you have logical channels. No, those of you have studied microprocessor, etc. You have logical channels. Okay, 16 logical channels, 64 logical channels. Similarly, you create virtual networks on top of one another. Each slice is optimized for a specific purposes. Okay, ensuring that a critical task never gets slowed down by a non-critical one. So for example, let us say the common analogy to understand this is, say you have a big restaurant. Okay, you have a big restaurant, so where you have different types of food orders, isn't it? So somebody is ordering a very simple type of food. Let us say some simple, just a soup or something, or some let us say some samosa or thing, some which is going to be very easy to make, and many people order that because it's a cheap item, so many people order that. So so what will happen is that it's normally what will happen if you have a single kitchen, only one oven, you may be having a one oven cooking everything, then there could be some special orders, maybe some, it is coming from a hospital kind of patients where it's a very special type of menu where you have to be very careful about the amount of salt, sugar, or some special, some disease is there. So you, even if small mistake is there, the sanitation has to be very good and all those things. A special type of oil has to be used. So this is typically the emergency type of applications, like your robotics based industry applications. Suppose your manufacturing is going on, okay, based on some 5G network communication. So there, even small mistake will create a defective product. So those type of, so something a similar, a very sophisticated meal is being there. So, or for somebody very special, say for some very important VIP, the meal is being made. So you cannot have the same cook and the same this thing for everyone. Okay, so you have different type of three different broad areas. So you can have slicing of the networks. So it logically divides the physical network, and they are virtual logical divisions, not physical walls. So this kind of networks, and these two are very, very related technologies. If you have not heard about it, at least try to understand, because this is how it works, the 5G network as a communication network. One is the physical layer, and especially, and one is the control layer, the, I mean, data access, and especially when you do the physical, beyond physical layer, there has to be a networking layer. That control has to be now done through software, SDN, and network function virtualization. These two are also very much related. Otherwise your 5G and 6G will never be a success if we are not doing the function of network slicing. So I'm just trying to give you a flavor of what are the different things. Now this is more or less about 5G. Now, when we move to 6G, 6G is also round the corner, and most of though are still not under very, very strict deployment. But then it takes, those of you are going into research at this stage, 2025. So when you are going to submit your thesis, so it's beyond another 5 years. Already some of the advanced countries will have implemented the 6G. So it is very important for us to understand the 6G evolution. Please note that we are going now, when we go for 6G, once again, we are expecting that even your 5G will exhaust my millimeter wave. So in that electromagnetic spectrum, we will have to still move into the higher frequencies. That means your 6 millimeter wave is typically around 30 gigahertz or less than 100 gigahertz. Okay, less than 100, typically 28 gigahertz, 30 gigahertz, within that range my millimeter wave deployment or practical this thing, usually the design is actually stopped till now. But then beyond 100 gigahertz to 1 terahertz, it is the beginning of what we call the terahertz or sub terahertz frequency. Once again, the moment we have a wider bandwidth, you have a wider bandwidth now, even 10 gigahertz instead of 1 gigahertz, 2 gigahertz, you may have 50 or 60, 50, 60 gigahertz, 20 gigahertz. So it's almost 10 times of bandwidth available. Obviously, from gigabits per second, from in 5G, we'll move 4 terabits per second. And you will have revolutionary applications are coming around. I think we have wireless brain computer interfaces, human and robot interfaces, human like robots, where if those who are interested, you can already, maybe we read in newspapers and different places already this area. So this is not possible unless you move to the 6G and terahertz communication. Here you can guess that the challenges, I already told you about the challenges in millimeter wave. Now here the challenges will be even more, because the propagation law, more is the frequency, more will be my loss. So you need more advanced techniques in terms of the materials that you are going to use, circuits, because I need to use A to D converter, D to A converters. No, this is a huge bottleneck, because sampling, when the moment I do DSP, because most of my signal processing will be happening in the digital domain. So whenever we have DSP, I have to go for A to D and D to A converters. Now sampling, the more higher is the bandwidth, my sampling frequency has to be higher. It's very, very difficult to design. Circuitry becomes very difficult. Which materials are you going to use? Okay, because ultimately you have to fabricate them on ICs and all when you are going to create such embedded systems. No, there are a lot of, so these are the areas where researchers or terahertz communication people, whoever works in their domain, they are researching all. Large bandwidth, okay, once again. So 6G evolution, we will continue to use the other technologies that I told you. So never imagine that 5G means end of something and 6G is beginning of something. It is the same technology will be remaining, but then advanced features are continuously being added. It's something like the base of the cake is already there. You are continuously adding, making it more decorative with more layers of cream and other decorative things to improve the value addition. But then you are getting a lot of benefits. At the same time, you have to solve many research problems, and these are mostly in the research stages. So wider signals now provide high resolution. This is another very important applications of this. When I'm going to use higher frequency, what happens when you use higher frequency, millimeter, terahertz, etc.? What happens is that it's something like when I use a wider camera. Okay, it's something like your sensing power improves, isn't it? I'm using the aperture of the camera is small. You all understand the power of the camera. We are so obsessed with the cameras in our mobile phone. We want a very good camera. Naturally, a wider view of the camera is going to give you a much more detailed photograph. Similarly, when I'm having a wider bandwidth, the resolution improves highly. Okay, so you are able to distinguish objects that are very, very close together. I was telling you, even in crowded places also, you can have excellent Wi-Fi kind of Wi-Fi communications. Massive MIMO, as I told you, we already discussed the importance of highly precise beam forming and angular resolution. Okay, angular resolution is the beam width. You have the beam width, you just has a bandwidth. You have the term beam width in antennas. So the beam width, it can be very, very small angles. The resolution of the how much angle the antennas can actually be, because we are now doing it in the form of your IC antenna. So antenna technology is a very important part. Okay, how to pinpoint in a particular direction. Millimeter wave or terahertz, you have tiny wavelengths. The signal, I think this point we noted that signals are almost acting like a light. They can travel in straight lines, reflected. So lot of, just like we have optical microscope and things like that, they are based on the optical properties of light. So these high wave frequencies, they behave something similar to light. So here also there is a scope of making a lot of instruments and all with for fine grained details of the environment, because the electromagnetic wave is passing through the environment. So a lot of resolution, you can have interesting applications in this. The 6G evolution is related to the 5G thing. Okay, advanced MIMO from MIMO is also now advancing. Okay, massive MIMO these days you will hear about XL MIMO. It is extremely large MIMO. So moving from, I told you 264 is the number of elements that we are limited in the 5G. Now we move from 264 to almost more than 100 and thousands of antenna elements. Same benefit, but then other signal processing challenges will come. From massive MIMO, now in the 6G we are moving to XL MIMO. Okay, new architectures will come. These two are very important. Okay, so later on maybe you can Google and find out what are these. So these are actually the directions in which the new architecture is going. I've just listed, there could be a few more, But the most promising one, which is already crossed the research stages and is on the verge of practical deployment and integration in your what you call your 5G standards, 6G standards, 5G standards and all, we are moving towards holographic memo. Holographic memo means the entire surface. Example, a wall can be treated as a continuous radiator or receiver, not a discrete array. So this is a very interesting application that your you are giving more powers are coming to your signal. The signal earlier, the signal in 4G and all, the signal was just being used for communication. Now you're using the communication transmitter or the receiver. Ultimately, you are having a transmitting antenna and you are having a receiving antenna. Now they are all antenna arrays. Now you can use them as a very powerful electromagnetic sensor also. So they can actually sense when they are traveling. So the type of electromagnetic whatever emission is happening, they can actually make a different dimension to my this thing. They can create an image of wherever they are passing. Suppose the electromagnetic wave is passing through a building, it is passing through a tunnel, it is passing through the metro station, it is passing through some bridge. So all the maybe a river or a mountain. So they will actually be able to carry those information with it, and you can almost create an image, a hologram of what the entire environment looks. And many interesting applications are based on this. Then you have what you call the RIS. Have you heard about it? It's called, some people write it as IRS also, intelligent reconfigurable surfaces. Okay, or programmable surfaces. So this is something like creeping some mirrors. So suppose what happens is that, suppose the signal is, and this is specially needed in case of my millimeter wave propagation, because your signal cannot travel a long distance. So maybe there is a block. Suppose there is a big building, or not even a building, let us say there is a small wall. And as I told you that your millimeter wave or the high frequency wave is not able to pass. It cannot penetrate. Penetrating power is low. It cannot diffract. Some corner is there, like your low sub 6 gigahertz signals. They can actually pass, bend around corners, diffraction, etc. But your higher wave signals, they cannot. They behave more like light, just like light cannot pass through a wall or something. So similarly, they cannot pass. So what do? You have, but they can be reflected. So you create you keep something like a mirror. Okay, this mirror is going to reflect the millimeter wave. You cannot see because still it is not coming under the visual range, but its property is very close to the light, visible light. So but you can create some artificial mirrors. Okay, some painted surfaces, maybe on the wall itself or just behind the wall or somewhere you can, because this is where it's creating blockage. So I can keep a RIS surface, maybe some some just on the street lamp or something, on the billboard, advertising billboards are there everywhere. So on that little bit of surface you coat, so this is going to act like a mirror. So they are going to actually intelligently, it's going to be reflecting and shape the wireless signals. So it's going to create, so the entire till now my antenna transmitter and receiver were being smart. Now your environment is also being made smart by giving these kind of surfaces. So this actually, wherever you have dead zones, blockage, okay, dead zones and blockage, low penetration, this is very typical for millimeter wave and terahertz. So this will help you to overcome this. So there is something acting like a relay, so the surface is going to reflect it, just like the satellite. You cannot send, there is a big sea in between two countries. So what do? You send a signal to the satellite, it reflects it back to the other part of the world. So this is something like similar to a satellite, small, and it's a passive element. You don't need much power. So some metamaterial surfaces are there. So they can actually, once again, the function is same. It is changing the phase shift of the electromagnetic signal. Something similar to beamforming. So it is adding my beamforming technology. It's a next stage of technology enhancement. And as a result, your cell boundary is very large. Now there will be what you called, there will be no need of a cell now. Your cell becomes now free. No cell, or we got cell-free MIMO, we call it. So now, because everywhere, wherever there is a problem, typically you are taken care of. If my signal is getting a blockage, it's something, we all know signal boosters kind of thing. Okay, signal boosters is something, it is similar to a signal booster, but here this is a passive device. So excellently, without expending too much energy, we can do this. So it's also a very interesting area, because of which my 5G and 6G technologies are going to be made strong. And of course, this I think everybody knows or might be hearing that the second leg of evolution of 6G is its deep integration with AI ML. Whenever you can, by whatever little bit of topics I have discussed, you might be actually realizing that the problems are getting complex. You are getting more benefits, but the problem is getting complex. So whenever we have complexity of the problem increases, okay, managing thousands of elements. Now I told you thousands of elements, antenna elements will be there in your terahertz beam. It is impossible with traditional algorithms. So a paradigm shift, you have to adapt the AI ML technologies, because your channel estimation, RIS I was talking about. So these are the broadly we have for beam management, beam management is that you want to, I was telling you, na, the user is moving. So the moment the user is moving, the beam also has to move with it. So beam switching, beam tracking. Okay, so this cell-free massive MIMO mein, so you need strong AI/ML algorithms. Channel estimation, huge overhead for channel estimation needs to be reduced. AI can control the RIS elements. This is also a lot of optimization is required. Signal processing has to be made simpler, or training may be required, learning. Okay, because every now the environment is also smart. So future 5G standards, the current deployment already maybe if not the current one, but at least the latest, the developed nations which are working on the next 5G standard or advancing the 5G standard, they already have, you can see some of these topics where already the key ML algorithms are already major vendors like Ericsson and Ericsson, Hoover, and all those big multinational companies, telecom companies. So they have already, you can see they always are, some of them are already deployed, some are under the trial phase, some are still under the research stage. So you have these are the machine learning algorithms which are typically used. Channel coding is a very tough topic. I told you, na, network slicing, little bit of idea I gave you what is network slicing. Every different type of applications you try to separate. Just like we were giving you that analogy of the kitchen. Different types of food orders have to be given different type of cooks and different types of places in the kitchen. So similarly, my network has to be designed. So this is also a very complex thing. This is also not yet deployed. Okay, the last three. So CNN and all that, these are the, anybody wants to go directly into the working to the ML models used in wireless communication, you can go through some of these literature. Okay, individually, these are all huge research areas. But you can notice that already major vendors have deployed some of them. RIS. Quickly, we'll be talking about, as I was telling you, RIS is something like as if you are putting somewhere a smart mirror anywhere on the environment, maybe on the wall, on the ceiling, or some advertisement board. It's not an ordinary mirror. You can actually program the mirror to reflect the light waves in any direction you want. And you can even control how it is going to affect the other waves. So it's a very powerful approach, okay, which we call the software defined surfaces, and its implementation is not very costly. It is very under deployment. Okay, it's RIS is not currently a standardization part of your 5G, but it is a very active area of research, and testing is going on for 5G advanced and 6G networks. They will employ what is RIS. So those of you who are starting research in this area, want to get into the domain, you cannot avoid the use of RIS, because in 5 years time, by 2030, this will definitely be coming as a deploy under the deploy stage. So just see the difference between traditional wireless and the RIS enabled wireless. The environment is a passive and often hostile. There are many obstacles that blocking, reflecting, scattering unpredictably. Now with RIS coatings, RIS materials, you have a total control of the environment. So you can now program how signals will be reflected, and you can use it to your advantage. So this is an additional tool. In addition to beamforming, I can use my beams can be actually directed through an RIS to make the whole thing very effective. Okay, how does it work? There are basically three steps. So whatever communication model you're using for 5G 6G, I think you have to incorporate the element of RIS. So it works the free. Once again, I've avoided mathematics, though the mathematics is not very difficult. It's only about how you change the phase angle. So you can reflect, reconfigure, and smartly direct it. So by carefully controlling the phase shift of the wave reflected from each tiny element, the entire surface, as I told you, you can constructively interfere so that at your phone you receive the strongest signal. Okay, please note that it's creating a very strong focused beam. directly at the user like a parabolic antenna or beamforming, but it is done passively. So this can go without beamforming also. There are ways to combine it with the beamforming, but this is a parallel area of technology development which is going in the advanced 5G and 6G. Okay, so now we are coming to the end of our presentation. So as we are moving from 5G, you can see 5G began with, let's have a quick recap of whatever we have discussed. So we have a, quickly, we have actually talked about your, basically 5G is about, the main foundation is lying on the use of millimeter wave channel frequencies and your massive MIMO, and how we are actually needing both. In spite of that, I think, as I told you, as we are moving from extremely large MIMO or XL MIMO, at the same time, my frequency is also going. Na? जैसे millimeter wave hertz के साथ जो है, with millimeter wave, we were going for massive MIMO. Now here, what we have is, we have extremely large MIMO, and along with that, we have hyper MIMO or terahertz frequencies. So we are moving from millimeter wave to the sub terahertz band. Look, please note that sub terahertz band. It is 100 gigahertz to 1 terahertz. At this frequency, you could be used again very high resolution. I was telling you, na, we have an additional, because of the very high frequency, they can be used as a very, you can get the image. It said that almost you can see the entire environment. So whatever path your signal has been, suppose your base station is at 100 kilometers away, but when your signal is coming from your base station to your mobile station, the entire environment through which it has come, you can sort of get like a radio environment map or a image. Even visualizing is possible, okay, through instruments, of course, because directly we cannot see. So you can actually visualize millimeter wave signal, because the physics wave and even terahertz signals. So you have network scanners and receivers, specialized hardwares. They can actually measure the power and create a map of the coverage. You have RF cameras and imaging system, highly sensitive device. You know, this is going to create lot of very, very interesting applications already. I mean, those who are dealing with very good high tech technology. So they are actually beginning to use, for example, they can be used for very powerful security screening. They are much powerful than your X-rays. The kind of, you know, you have seen X-rays, this thing at airports and all, where our luggages, etc. change. Something similar, they can have a very good powerful. So there are a lot of another, other than communication, as I was telling you, they are acting like your imaging and sensors. Okay, so a lot of scientific research is going on. You can study the antenna patterns, how millimeter waves can be used in a lab setting. So a lot of research is going on in this area. Okay, digital twin. Another very, those of you are using the buzzword in the case of your what we call your machine learning and AI. Digital twin is a term you will use. Digital twin means it is a bridge between the physical and the digital world. So it is possible whether now you can optimize, analyze the predicting the behavior of the real world through a virtual mirror. This is a very powerful architecture which you can do. So digital twin is also something, if you are going to the next era, advanced 5G and 6G, in the network architecture, we must have a digital twin architecture so that that can be controlled from somewhere. I was telling you, software defined network, network slicing, function NFV, function virtualization. Something like very simple to a very good analogy that we sometimes have. Suppose you are there in an airplane. So as long as it is in the air, the physical plane is the one, physical world is actually one which is flying through the sky. But on the ground, the control system, suppose you have the control room. So you must have a perfect virtual simulation of the exact plane on the screen. Now this is not a pre-recorded video. The live data from hundreds of sensors on the plane will be there, okay, for various parameters, sending the information about this, and they are going to create the, perhaps, maybe suppose if we have this kind of a digital twin, we could have actually predicted what happened when the aircraft crashed. See, we rely only on the black box, isn't it? But if you have a powerful digital twin, so wherever the path of the plane is going, you can have the digital twin. You have the real life data of what is happening of similar kind. So this is what we call the bridge between the physical and the digital world. It is called the digital twin. Similarly, for your, when I'm transmitting something, I must have the digital twin of my entire environment. So based on this, lot of applications are coming. Okay, some of the examples you can see the moment, because see, when we go for advanced 5G and advanced 6G, it is the application which is important. For example, digital twin. You cannot, most of the domain that I have outlined over here, that this is the digital twin purpose. For example, in manufacturing production with high sophisticated manufacturing production lines, okay, you have to simulate the production flow for bottlenecks and maximize output. Very automated plants, big complex plants. Healthcare, you can see the patient's heart, some surgery, etc. You are making a remote surgery, or some patient, a serious ICU patients, so many sensors are actually monitoring so much. So you get this thing, somewhere the doctor may be somewhere else, but they will get the signal that, okay, that this person is going to, some problem is there or something like that. Okay, so entire twin of the model of the patient's, whatever may be heart, kidneys or whatever. Smart cities, cars, your power plant, smart grids. Okay, so these are the kind of applications. So here 6G will this a term now you will see, it's called integrated sensing and communication, ICS, or joint sensing and communication. The signal that the future network will act like a nervous
sensing and communication bole. Joint sensing and communication bole na.
Joint sensing communication bole hote kya? Okay. Integration also is something.
Okay, sorry.
So this means future network will act.
Hello, Devjani ma'am, you mute yourself.
I don't know how. Is it okay now?
Yes, ma'am.
So as I was telling, so this is joint sensing and communication is one area that is sort of, it is a new paradigm where I was telling you now, wireless network is no longer is carrying data. It has the ability to see. See doesn't mean exactly the visualizing, because it's not coming under our visual spectrum, but there are instruments which can actually see or visualize, create a map of what is happening and understand the physical environment using the same signals that you're using for communication. It is something like a sixth sense to the 5G and 6G. Okay, a device is sending signal to the base station. This is part of it is only a communication. The rest of it, the signal is getting reflecting from the objects in the environment, cars, people, drone, walls, everything. Okay, the base station is receiving echoes, so they will analyze, just like you have your radars and sonars, so you can analyze many things: angle of arrival, Doppler shift, range, velocity, angle, what is identifying the objects, what type of objects. Maybe there could be a car, there could be a mountain, there could be some other kind of objects, because or some other material. So this is typically the signature means every object has got a different type of signature. So it's a very tremendous, huge role of application where you are using the same signal as a sensor also. And this can happen simultaneously with the normal data transmission. So this is what I would like to end over here. I just tried to give you a broad idea about what is the days are coming ahead, especially in terms of research challenges and other things. So I'm open for questions. We have about 10 minutes time. So if anybody is interested, anything, if I know the answer, I'll try to help you out, because these are very new topics, and to conceptualize is definitely time taking. So those of you who want to work towards your doctoral work or higher studies and all, so you need to give some time. But then there are a lot of tools, and in the open domain, research domain, a lot of papers and all available. So it's an interesting area, and it's definitely new areas. So I'm open to questions now, if any.
Good evening, madam.
Yes, please.
I'm Chandrakala from Chennai.
Yeah.
Madam, my
question that you told that reflective intelligence surface deployment of RAS. My question is, will you please suggest some research problem in that area where we shall move forward?
Okay, so now see the research problem. I told you RIS is affecting many things, isn't it? Whatever communication, see, the problem is that moment I'm going into RIS, the frequency range is important. Okay, so maybe suppose you are working in channel estimation. Suppose you are working in capacity optimization, resource allocation. So whatever conventional classical problems are there in your wireless communication, everything needs to be reanalyzed, remodeled when you move a system with RIS. Okay, so it's basically transmitter RIS. So you are free to choose any area. You look into that, look for some survey paper. It's not that everything changes, na? If you are going taking a terahertz communication, so channel estimation will work differently. So because the channel property is changing. So now with channel property, there are so many associated things. If you are working on some modulation schemes, channel coding schemes, everything will change. So everything is a new research topic. So whatever area you have been working in the conventional, I will suggest you, it's better you move into that domain only, how to extend it in the millimeter wave channels or terahertz channels.
Okay, madam. My question is, if we are going for a channel estimation, here two channels are there. One thing
Yes,
from
yes.
the handset to the base station, from
Yeah,
base
right.
station to the reflecting surface, and reflecting
Exactly.
surface to the user. Then which end of communication that we should concern about?
See, you have to consider a system model. So whenever you're going to do some work, na, you take some basic paper. Okay, so there they have a standard system model. Okay, so now suppose, as I told you, now what is your end goal? You are trying to investigate the impact of a channel estimation algorithm. Let us say MMSE. Suppose, for example. Okay, so MMSE without RIS, MMSE with RIS. So now you have to realize. So everything has to go there, and they are all not explored because it's not yet deployed. So, for example, earlier you had cooperative relays, isn't it? So cooperative relay is a much simpler technology than your RIS. So, but it is similar to a relay, isn't it?
Yeah.
So maybe, okay. So as I was telling you, any problem domain that you want to adapt, you can do. But then you explore the normally way you try to find out the research papers and all what happens. So it's better you, if you at your master's level, are you looking for a PhD level problem?
Oh, madam, I have completed the PhD and for moving forward in this particular research
So
area.
you want to give some project, or you want to give write some project, etc. That's what I'm saying. Na? These days the move is towards deployment. So you try to see. I give you some idea now. So which are the not yet deployed areas still now?
Okay.
So you search those areas, and then most of the, if you are looking for some good R&D projects, so try to see which are the areas where it's still under research stage, and try to move in that area.
Madam. Madam, these modules can also be simulated using MATLAB, is it no, madam?
Yes, you can.
Yes. Okay,
You
madam.
can, because ultimately everything you will be simulating because see, what is RIS? RIS is not very difficult thing. RIS is something, it's basically a mathematically, it is basically changing the phase shift. Basically changing the phase shift. It's a phase shifter.
Selecting that particular crucial phase shift is also a matter
it has
of
to be
concern.
related to beamforming. So you have to align it with the beamforming and those if you are working with RIS. So maybe, or you do not want to use beamforming, maybe only RIS. Okay, depends on the problem model. You select the system model in which you have reported results, in which maybe some already existing codes are there. So that will give you a base to start your work. Then on top of that, you can do any type of analysis. Most of them are not explored. So if these areas you touch upon, they will definitely be a new area.
Okay, madam. Thank you, madam. Thank you very much.
Okay. Thank you. I hope it was useful. I don't know. It was useful to how many? Pradipto, I think I can, please unmute. Hello? I cannot hear you. Pradipto, I cannot hear you. There is somebody asking or raising a hand. Can you hear me? Hello?
Hello, ma'am. Good evening,
can
ma'am.
you hear me? Yes, please tell.
Actually, ma'am, I am a management student, but I have a question regarding a factor. When you select a flight, there I see that only credit card wants, not debit card. Why is that? I have asked this question to many, but nobody answered the question.
What is the question? Maybe
In
your
the
why credit card works. First of all,
only
I'm a very person away from this kind of credit cards. Frankly speaking.
actually I also don't own a
Okay,
credit card,
okay.
but
But
I have to. matlab, I want to know the answer. Actually, I am too much interested why that particular credit card works on slide but not debit card.
okay, so I think the answer lies in the type of network that is because see these networks. See, I was telling you, na, the at one level. See, any computer networks. If you are having the computer network background, so there are different layers in which a telecom network works. Okay,
Okay.
so maybe the financial applications. What I guess is that I'm not able to give the entire answer, but what I guess is that you have the networking. If you see, if you are from technical background or those of you are there, so you know that there are different layers in which it works. So this normally will come under the what you call the application layer. Okay, the last layer. So the application layer is very much application specific. So it depends on the service provider, whoever is having that. The credit card financial companies or whoever, I don't know that. So there it is an application layer. It has got nothing to do with the lower technology. So there, for example, somebody has some password system for accessing, somebody has 2 levels of password and all. So it is an individual service provider. So they have already disabled the service of debit card because for security reasons or something. It is totally dependent on the application layer network. Okay, so there it has got
Okay,
nothing to do with this one.
it is nothing to do with technology, right?
Nothing. So it depends on what type of. See, somebody is giving a Zomato order and somebody is actually making a banking transaction. So probably the banking transaction of huge amount. Definitely the level of this thing will be different, isn't it? So the application layer that we call the 7-layer architecture. So definitely that design is there. And as I was telling you, these days are it's a control network is separate from the data network. So the control network is given to different service providers. So that way I think it works. So there they are not providing this kind of service maybe for because credit card things are happening in a different way. Na? There is unlimited transactions you can do and all those things. So that is why it is happening. It's nothing to do
Okay,
with
okay.
the
Thank you, ma'am.
internal technology. It's the highest layer, application layer different. Anything else? Anybody else?
Okay,
Yes,
ma'am.
Pradipta. Yes,
Yeah,
please.
am I audible, ma'am?
Yes, you are.
Actually, there are two small questions are there. The last one, also by next session guest is also waiting, session speaker. The first question is from Dr. Sangita Roy. The research software and practical point of view of the labs. And second one is, please suggest some AI/ML algorithms to optimize the RIS from Loganathan M.
Okay. See, that's at the see. What I'm telling is that I showed you one of the slides in which I specifically see there are n number of people working in ML AI. So there is not a specific algorithm. So you need to do the literature survey. So you are if you want, nobody can tell you that this machine learning algorithm is going to be suited for this RIS. So maybe for RIS we will find all starting from, let us say, these days you have deep learning. In deep learning also there are so many architectures. So whoever has worked, you have to only work it out and find out how it works, or you have to do the literature survey and find out. This is not a straightforward question that okay, this machine learning algorithm works for this particular problem, RIS. So you need to do in fact, that will be a part of your literature survey. So if you want to optimize some RIS related communication, so you need to do the machine learning algorithms. Maybe our reinforcement learning is working or LSTM is working. So you'll find 5 papers having LSTM, another 10 papers using a what you call a deep learning architecture. So you have to go through all and then take the call which one is this. So this whatever question you have asked, I think this cannot be generalized for any problem domain that this machine learning algorithm is good for this. Okay, so you have to find out the literature survey and do it, and perhaps do it. Yes.
Okay. Thank you, ma'am, for your informative session on 5G and 6G communications. And at the end of the session, I want to felicitate you with our small memento. Please accept it, ma'am.
Okay.
We'll send you a letter in your email ID.
Okay, okay. No problem. Okay, please. Somebody is waiting, huh? Okay, thank you so much.
Yes, yes, ma'am.
Thank you so much.
Thank
I
you,
hope
thank you,
my
ma'am.
only thing is that I hope the audience have actually gained something, little bit of information for which is useful to them. And I wish you all the best for patiently listening to a 1.5 hour lecture, especially in the evening time. Okay. So my email ID, etc. Yeah, they are publicly available. Okay, and yeah, and Dr. Pradipto has been my student, so you can get other information from him. Also, I'm open to any type of help. If my knowledge can help any of you, I'm most willing to share it. You can contact me by mail or otherwise. Thank you. So I'm leaving the meeting. I'm leaving.
Yeah, yes. Thank you, ma'am.